Hi, I'm Chris Owen, CEO of Voxa, based in Seattle, Washington. I'm excited to share with you the innovative products we at Voxa are providing for the connectomics community, facilitating progress toward whole brain circuit maps. Voxa technologies have facilitated some of the largest and most rapidly acquired imaging datasets in the world. This technology comes from a history of experience with TEM, automation plus industrial scaling, and also developing complete end-to-end high-throughput pipelines for genome mapping using EM and aberration correction in the mid to late 2000s. The genomics project Voxa was involved with wound down when other technologies eclipsed EM-based gene sequencing in cost. So we turned our sights to bringing the accessible, detailed, and incredibly fast nanoimaging and sensing we developed for sequencing to a wider range of fields. Today, Voxa's mission is to advance humanity through nanotechnology, transforming analytical nanoscale imaging to make it more accessible to a larger pool of scientists, engineers, educators, learners, and the public around the globe. We're here with you today, focused on the application of our high-throughput blade system to help realize the goals of the connectomics community to map the whole mouse brain. But our overall mission as a company is about accessibility. In connectomics, in biothreat detection, in field sample analysis, in pathology and medical diagnostics, and other fields. Outside of connectomics, one of our proudest accomplishments is placing the first EM in space on board the International Space Station. As one of the most extreme research environments currently in use, our award-winning coffee maker-size SEM, Mochi, is a great example of our mission to take nanoimaging to places it has never gone before. ISS is the only microgravity research platform in the solar system, and Voxa operates one of about a dozen national laboratory facilities on ISS, supporting microgravity research. Rodents and flies are a huge part of research on ISS, and NASA and Voxa together welcome your proposed research in microgravity using newly available EM capabilities on orbit. So, come look at fly brains with us in space. Let's talk about application of Voxa's blade platform to connectomics. The Voxa Blade product line provides the diagnostic power of TEM with the speed of cloud computing. Blade is fast, sensitive, and flexible, and built from the ground up for remote operation and scaling. It has proven results from petascale neuroscience tissue imaging projects with leaders in the field. Here is Blade in action. This video shows real-time acquisition on a Blade node at the Princeton Neuroscience Institute, courtesy of Jihao Zheng. It demonstrates blade acquisition configured for greater than 400 megapixels per second continuous operation. This time slice is part of a fully automated customer-specified sequence that completes 1 millimeter squared acquisition every 7 minutes. The tool provides for rapid visualization of large areas at both high and low magnifications for inspection and continuous process monitoring. An example of the acquired image is shown at right and is representative of typical imaging pipeline output. As part of scaling, we provide a key technology called Cricket, which supercharges the TEM. It uses a hybrid parallel serial beam jumping modality to increase acquisition speed by up to an order of magnitude. In the traditional step and settle fast EM imaging paradigm, the microscope is idle for half of the time or more. This is sobering. Cricket increases its duty cycle to 90% or greater, eliminating the step and settle overhead by multiple factors. We've demonstrated Cricket's efficacy, clocking sustained speeds greater than 600 megapixels per second at customer sites, with ample signal-to-noise for the application. So with one blade on one TEM, you can produce large datasets routinely. But what if we have a fleet of blade TEMs? We designed these systems to be modular and affordable. A fleet can start with a single node and then can grow on demand incrementally as user needs expand. This scaling has already been done at customer sites, and we are continuing to improve the technology to scale larger. Currently, we offer two flavors of blade solutions that provide complete automated imaging together with robust automated sample loading. One flavor delivers samples on hard substrates, and the other delivers samples on soft conveyor belts. Different levels of scale are enabled by these products, providing for pipelined workflows as high as 1 million times faster than conventional manual ones. This video is of the automated sample delivery and low magnification overview imaging of samples delivered by soft conveyor in the TEM. The sample is suspended on a thin polymer membrane, and the image is scanned rapidly onto the detector after sample transfer. This enables rapid high-contrast overview capture of each tissue sample as fast as once every few seconds, providing rapid-fire information about the sample at the micrometer level. This provides EM-level survey contrast with very low overhead. Here is the model workflow for this class of scalable pipeline. Our role is to meet you at the critical conversion point where the atoms of your sample are converted efficiently into digital bits. Part 1, above, is the physical portion, and Part 2, below, is the digital portion. Blade is your transducer that converts between these two domains. An important observation is that Part 1 steps are irreversible, whereas in Part 2 they are effectively infinitely reversible. Robust archival media for the TEM uniquely enables revisiting samples after initial acquisition, providing maximal value from the time and effort that was invested in Part 1. Blade enables reliable and robust sample delivery, both random access and sequential, making it a perfect vehicle for future explorations after the initial acquisition. We have a lot to look forward to. In the past, the fruit fly hemibrain took about 2 years to acquire. Later, the IARPA millimeter cubed, about 1 to 2 orders of magnitude larger, took just 6 months, utilizing Voxa sample delivery. Based on our calculations, we expect a whole mouse brain could be acquired with about 100 blade TEMs in the span of 1 to 2 years. We believe that with commoditized imaging, the rate-limiting step returns to sample preparation. At Voxa, we're working to roll out a red carpet for our customers and collaborators, with the aim to make TEM at scale routine and turnkey. We think that by making these new solutions more available, EXASCALE NEUROANATOMY is now enabled and ready for next-gen science. In summary, first, TEM-based connectomics is fast, currently at several hundred megapixels per second per node, with room to grow. Also, its media is inherently archival, meaning it's forgiving of mistakes, but also enables future study at greater detail. It's fully automated, but also scriptable by API, freeing the researcher to focus on experiment design, data crunching, and optimization. And finally, Blade is designed from the ground up to be modular and affordable, making it suitable both for a starter lab and for growing needs of established institutions. These advantages open up broad new avenues for creative experiments at scale. In closing, I'd like to thank our customers and collaborators, and also I'd like to share that Voxa is hiring. If you're interested in a role building next-generation connectomic tools with us on the industry side, or working on democratization of nanotechnology tools, please let us know. Thanks for listening.